board to this computer. That's what I did. Okay, so let's do a couple of examples real quick, and then we will work through some problems that are in the homework. So I first want to look at this example. So find all homomorphisms C from Z4, Z2 cross Z2. Okay, so here are some facts to keep in mind, just to really check off the boxes of everything that we need to do for this problem. It's good to keep these kind of facts in mind because it can really like cut down on the amount of work that you have to do. So the first one is that Z4 is generated by 1. In other words, it's cyclic. So that's an important fact for two reasons. And so one of the reasons is that we only need to describe P of 1. In other words, the image of the generator under the map. So there's a homework problem or something. I think it's in the homework, where it follows very quickly from the homework problem that says that if you've got a homomorphism of the cyclic group, then a couple of things. First of all, that homomorphism is completely described by what happens to the generator. And secondly, the image of that homomorphism is also cyclic. So let's recall that the image of a homomorphism will be a subgroup of the codomain. So that's our kind of next fact under this heading right here, because it's kind of related. I'll write it like this, maybe phi of Z4, which is also like we could write as the image of phi. So that's like the range of the function. So not the codomain, not Z2 cross Z2, but it's going to be whatever is landed on is cyclic. So yeah, okay, and that's because Z4 is cyclic. The image of a cyclic group is cyclic. So that's cool. And then maybe like another fact, real quick, under this heading as well, is Z2 cross Z2 is not cyclic. So I mean that's pretty clear. Like it's generated by two things, 1, 0 and 0, 1, right? This is the only group of order 4 that's not cyclic. So this gives us something immediately, which is interesting, and that is phi can't be onto. It can't be surjective. Because if it were surjective, then that would prove that Z2 cross Z2 is cyclic, right? Because if it's surjective, the image is everything, but the image of if the image is everything, then Z2 cross Z2 is the image of a cyclic group, which means it's cyclic. Okay, so there are some facts involving the cyclicity of Z4. And then another thing, which is something we talked about last time and we used for a couple of examples last time, had to do with the order of an element versus the order of the image of the element, right? And we had some divisibility condition. So let's recall that the order of phi of G must divide the order of G. Right. That means the order of G is a multiple of the order of phi of G. So let's see what this means in our case. So this means that the order of phi of 1, and remember, we only really care about phi of 1 because Z4 is cyclic, so we only need to see what happens to the generator. The order of phi of 1 must divide the order of 1. So remember, the order over here is happening in the codomain, so that's Z2 cross Z2. The order over here is happening in the domain, so that's Z4. So what's the order of 1 in the domain, which is Z4? So how many times do you have to combine 1 with itself additively before you get to the additive identity?
One, right?
You're thinking multiplicatively. So what's the additive identity in Z4?
0,
Additive identity. So
0.
0, right? Yeah, because like you add 0 to anything and you get back to what you started with, right?
Yeah.
So how many times do you have to combine 1 with itself with addition to get back to 0?
Once.
No, 1 plus 1 plus 1 plus 1 is 4. 4 is 0 in Z4,
No.
right?
Okay.
So the order is 4. There we go, like that. So we know that the order of phi 1 has to divide 4. Okay, so, but we only 3 numbers divide 4, right? 1, 2, and 4. I mean, because it's the sum of a prime, right? Or sorry, the square of a prime. So in the end, so this is like kind of a summary of everything over here. This is like where your solution would start if you were writing a solution. So so maybe we would say like this: because Z4 is generated by 1, we only need to describe phi of 1. Also, we have the order of phi of 1 is in the set 1, 2, and 4, right? Why? Because those are the only divisors of 4. So that follows from this pink line right here, right? So the order of phi of 1 has to be in the set 1, 2, or 4. And now we just look at each of those 3 cases, just one at a time. You can probably do it quicker, but this is pretty short. So there's not a huge advantage to like try to shave time off of this. I would just do an in-depth analysis of all of these cases. So we'll do case number 1, which is the order of phi of 1 equals 1. Well, in a group, there's only one thing ever that has an order of 1, and that's the identity itself, right? Yeah. So if the order of phi of 1 is 1, then that means phi of 1 is equal to the identity. So that tells us that we have phi of 1 equals the identity over here in Z2 cross Z2, but the identity in Z2 cross Z2 is 0, 0, because it's an additive identity, right? Okay, that's all you can do. That's all you can do. Okay, so now let's look at case 2, which would be the order of phi of 1 equals 2, the second case, right? But now we want to look for elements in Z2 cross Z2 that have order 2. So that means you combine them with themselves. I don't know what word to put there. If you're watching this on YouTube later, comment about how I just about forgot how to speak English. Okay, so we've got to find things in Z2 cross Z2 that have order 2, but we're in luck. There are 4 elements in Z2 cross Z2. One of them has order 1, and the other 3 of them have order 2. And any of those will give rise to a homomorphism. And so we could look at 3 little cases here, or subcases, like examples of homomorphisms that satisfy this rule. So we could take phi of 1 to be 1, 0, like that. So notice this has order 2 in Z2 cross Z2, because you do 1, 0 plus 1, 0, you get 2, 0, but in Z2, 2 is 0, right? So we're good to go. And then we can also do phi of 1 equals 0, 1, like that. And then finally, we could do phi of 1 equals 1, 1. So all of those have order 2, right? And now, I mean, there are a couple of reasons that we can say we're done right now. Well, look, that means we got a homomorphism from sending the generator to any one of the 4 elements in Z2 cross Z2, right? So there's nothing else we could do. But just to like check this other box another way, let's look at the case 3. Like I said, this is not necessary because we've exhausted all of the places to send 1 already, but it's useful to do this anyway. So case 3, just for kind of understanding of the whole situation. Case 3 would be order of phi of 1 equals 4. And we can immediately say this is impossible, impossible. So impossible because there isn't anything of order 4 in Z2 cross Z2. Everything has order 2 or 1. And then I'm just going to do this as an aside. You know, sometimes like you see things written in different notations depending on, you know, where you're looking at all of this stuff. I want to point out that this Z2 cross Z2, it's also sometimes known as the Klein 4 group, which has notation V4. So if you ever see the Klein 4 group, it's the same thing as Z2 cross Z2. They use slightly different notation. It's also isomorphic to D2, which is the symmetries of a rectangle, not a square, but a rectangle. Notice for a rectangle, you have 2 rotations, 0 degrees and 180 degrees, and you have 2 reflections, this axis and this axis. Notice that the diagonal axes don't give you a reflection because they would like flip this thing so it would be taller than it is wide. Anyway, those are all the same group. Okay. Okay, so does this seem good?
Mm-hmm.
Cool. All right, so let's look at another one. You guys all get my email of where to find these videos afterwards?
Mm-hmm.
Cool.
Yeah, you have the folder from on YouTube.
Yeah, that's correct. Randos have like happened upon them. Like my biggest fan. He's there. Okay. We got like 1,000 new subscribers yesterday. I don't know what happened. Okay, so let's do this. So let's define phi, or let's define phi from Z50 to Z15 by phi of 7 equals 6. Let's say that's our description of the homomorphism. And now, before we get into the questions, I want to do a little bit of analysis of this, which will actually help us with the questions that are built on this. So notice that the GCD of 7 and 50 is equal to 1, right? They're relatively prime. But that tells us that Z50 can actually be generated by 7, right? Remember, like we did this earlier, you know, I remember what it was like to be a student. It's like impossible to know what are the important things to latch onto and what are the, is just a tool that we're not going to use anymore. Well, it turns out that this is one of the important ones to latch onto. You know, it's a racket. Because I get to teach this class all the time, so I see what's important year after year, year after year. Anyway, you guys should be teaching the class year after year after year. Anyway, so here's what I'm getting at. Here's what I'm getting at. So Z50 is generated by lots of different things. And those different things are whatever is relatively prime to 50. So the canonical generator, which is like the standard generator, would be just the number 1, right? But you can use anything that's relatively prime to 50. So 3, 7, you know, anything that's relatively prime to 50. Okay, so that's one thing to keep in mind. And then another thing that we can notice is that the GCD of 6 and 15 is equal to 3, right? Would you agree with that? But that tells us that in Z15, the order of 6 is equal to, it's 15 over the GCD of 6 with 15. So that's we used that last time as well to find the order of an element inside of Zn, right? You have to do this GCD thing. So that's 15 divided by 3, which is 5, right? So that tells us immediately that the image of phi will have order 5, because we'll have 6, 6 plus 6, 6 plus 6 plus 6, 6 4 times, and then 6 5 times. We'll be back to the identity and we'll create this loop. Okay, so that's just a little preliminary analysis before we get into like looking at some more questions here. So let's say our first question is this: what is phi of n? Okay, so we know what happens to phi of 7, but we want to know what happens to phi of n. And I think the best way to do this is to find phi of 1 first. And then once we find phi of 1, we're okay. But how can we find phi of 1? Well, we need to find how many times do we add 7 to itself to get 1 in Z50. Well, I mean, we can calculate that real quick. So let's see. Notice that 7 times 7, which is 7 plus 7, 7 times, is 49, right? Yeah. But 49 is equal to -1. Right? So can we use that somehow? Is 101 divisible by 7?
I believe so.
So what we want is we want a number that is 1. No.
No, it's 14.4.
Okay, so let's maybe spell this out for just a second. So here's our goal. A number that satisfies 2 things. It's a multiple of 7 and it's 1 more than a multiple of 50. So if it's a multiple of 7, then that means we can easily write it in terms of the generator 7, right? Yeah. So that's why we want it to be a multiple of 7. If it's 1 more than a multiple of 50, that means it's equal to 1 in Z50. So let's just run through things that are 1 more than a multiple of 50 until we find one that's a multiple of 7. So maybe you guys try. So what we got: 51, 101, 151, 201, 250, so dial it up until we find one. There's a way to do this called the Chinese remainder theorem, but yeah, that right there. Guess and check. We got it yet?
No.
What are we at?
I'm at 238.
What's 238?
No, I'm still going.
No, don't do it like that. Do one more than a multiple of 50.
Okay, guys.
That's easier. There's less of those, right?
So as long as it divides by 7, we're good?
Yeah.
Oh, I got it.
What is it?
I think I did 301.
301 divided by 7. Yahtzee.
That was like the first one I tried.
So notice that 30, well, actually, let's write it like this. So 43 times 7 is equal to 301, which is 6 times 50 plus 1, which means it's equal to 1 in Z50. Okay, right?
I just realized that you said Yahtzee.
Yeah. Okay, great. But now we're good. Now we can easily calculate phi of 1, right? Remember that by 43 times 7, we really mean 7 plus 7 plus 7 plus 7, 43 times, right? So now we can do it. So phi of 1 equals phi of 43 times 7, right? Because that calculation right there is happening inside of Z50, right? But that's going to be equal to 43 times phi of 7, right? Because, well, that's the, by the fact that it's a homomorphism, right? We took phi of 7 plus 7 plus 7 43 times, and then we ripped it apart into phi of 7 plus phi of 7 plus phi of 7 43 times, and we just turned it into multiplication. Okay, but now phi of 7 is equal to 6, so this is equal to 43 times 6, right? But now we need to calculate what's 43 times 6 in Z15. So figure that out.
43 times 6 is 258.
Yeah, but in Z15. So 43 times 6 divided by 15. So
17.2.
yeah, but then we got to find the remainder. All right, so how do you find the remainder?
Like an old school long division.
Well, you can do 43 times 6 minus like 17 times 15. Yeah, that's it. Minus 17 times 15. That'll give us the remainder. So 3. It's got a remainder of 3 in Z15. Okay. Okay. So now, but now we're home free. Now notice that phi of n is going to be equal to 3n. Because phi of 1 is 3. But that means phi of n is like phi of n times 1, but then we're done, right? Okay, nice. So now let's look at some more. Okay, So next question is, what's the image of phi? Well, now that we've got phi of n is 3n, it's actually not too bad, really. We can just calculate phi of some numbers until we see a loop, right? So notice that phi of 0 will be 3 times 0, which is 0. Phi of 1 will be 3. Phi of 2 will be 6. Phi of 3 will be 9. Phi of 4 will be 12. Phi of 5 is 15, which is 0, right? Because we're in Z15. Yeah. So notice that we hit everything, like it starts looping after that, right? So that tells us that we've got the image of phi is going to be the set 0, 3, 6, 9, 12. Notice that's the cyclic subgroup generated by 3 inside of Z15, which is like pretty clear from the fact that it is equal to 3n, right? So phi of n is 3n. That kind of gives us that immediately. Okay. Now let's look at the kernel. Okay, so the kernel of phi, so that's going to be everything that gets mapped to 0. So let's recall that n is in the kernel of phi if and only if phi of n, which is equal to 3n, equals 0 in Z15, right? Okay, so let's see how we can calculate that. So what is equal to 0 in Z15? So that means that 3n is congruent to 0 mod 15. That's what it means to be equal to 0 in Z15, right? Yeah. But that means that 3n is a multiple of 15. Again, that's what it means to be congruent to 0 mod 15. So that's equal to 15m for some m and z, right? But now, like, notice we can divide by 3, right? So that tells us that n is equal to 5m for m and z. So that means n was a multiple of 5. But now we just want to look at multiples of 5 inside of the domain. Remember, our domain is Z50. So we need multiples of 5 in Z50, the domain. So kernel of phi is going to be equal to 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, and then we don't need 50 because 50 is 0 again, right? Yeah, so that's that. We've got the kernel. Now let's do one more. Maybe I want to point out that the kernel is always a normal subgroup of the domain. The domain is cyclic. That tells us that the kernel has to be a cyclic subgroup because every subgroup of a cyclic group is cyclic. So it might be nice to write this as the cyclic subgroup generated by 5. But that's kind of optional. All right, so let's do one more, which is actually like pretty related to what we just did, but it's useful to look at on its own because it looks a little different, even though at its heart, it's kind of the same. And that would be the inverse image of an element. So let's find the inverse image of 3. So phi inverse of 3. So notice I'm saying the inverse image and not like phi, and not like the inverse value of the function, because there's no inverse for the function. So this is the inverse image. This should be a whole set. Keeping in mind that the kernel is really the inverse image of the identity. So this is like sort of on the level of that. Okay, so notice we'll use the same kind of thing here for the definition of the inverse image. So notice that n is in the inverse image of 3 if and only if phi of n is equal to 3 in Z15. That's like the definition of being in the inverse image. Okay, but notice that we can define phi of n, or phi of n has some definition. Phi of n is 3 times n. So we need 3 times n to be equal to 3 in Z15, right? That's just by the definition of phi. Okay, but equivalence in Z15 is the same thing as congruence modulo 15. So that means we've got 3n is congruent to 3 mod 15. And you might want to look at that and say, hey, I can just like divide by 3, but you can't, because 3 is not relatively prime to 15. And you remember at the kind of beginning-ish of class, we saw when we had inverses modulo something, and we needed relative primeness, and we don't have that here. So you can't do that. But what we can do is use the definition of congruence modulo 15. This means that 3n is equal to 15m plus 3 for some m in Z. But finally, that tells us that n is equal to 5m plus 1 for some m in Z. Now we can divide by 3 because we're in the integers. We're not in the integers modulo 15. Now we can just like list a bunch of numbers that are of the form 5m plus 1. So one more than a multiple of 5. So we can say that the inverse image of 3 is going to be made up of all of these numbers that are one more than a multiple of 5 until we run out of numbers in Z50, right? So we've got 1, 6, 11, 16, 21, 26, 31, 36, 41, 46, and now we can stop because the next one is 51, which is the same thing as 1 because we're in Z50. Yeah, because we're in Z50. Now, this is not a subgroup. The inverse image of a random set may not be a subgroup. I think we showed earlier that the inverse image of a subgroup is a subgroup, but here we've got the inverse image of just the single non-identity element. That's not going to be a subgroup. So we couldn't write this as some sort of cyclic subgroup or whatever. It is like a coset for what it's worth. This is the coset 1 plus the cyclic subgroup generated by 5, which is 1 plus the kernel phi. Like something's happening there, but that's kind of neither here nor there. Okay, great. So let's maybe take a second and do a homework problem, and then we'll look over the homework problem so we can have some whatever time. Which tab?
3.7 plus tabs.
Yeah, you know it. Okay, so does anyone have the homework open?
I did earlier.
Just it's like a race to see who can get it open first. Because I just want to make sure that we all work on the same one so we can talk about it afterwards. You got it?
Chapter 11, 1, 2, 3, 4, 5, 7, 9.
Yeah, how about 9? 9 and 10 are assigned, right?
Yeah.
Yeah, how about 9 and 10? Well, I noticed I used 10 when we did one of these earlier problems talking about the image of a cyclic group, right? So it'd be useful to go over that one. So, but I want you guys to try it. And then we'll look at it. So 9 and 10, maybe 10 minutes for those two, and then we'll look at them. So that's our sequence of events. My nose is showing. My wife would call me straight out. She calls people out at the climbing gym. Your mask is not covering your nose.
Now you call your vaccination card, so I can do it all I want.
Yeah, I'm gonna cough in your face.
At most, I just want to do this because this is so sweaty.
Yeah, it's not so big of a deal. these. So this has to do with the image of an abelian group and the image of a cyclic group. So the first one says essentially that the image of, and we should put the word homomorphic, abelian group is, that's how we could say it like in words. The book has it written out with like a function type thing, which is exactly what we'll do now, and that's what we use in order to prove it. So maybe say it like this, i.e. if G is abelian and P from G to H is a homomorphism, then P of G, which you can also write as the image of phi, is abelian. So the range or the image is abelian. It doesn't say anything about the codomain. Notice that the codomain is all of H. That could definitely be non-abelian, right? Because we could miss lots of stuff. So let's look at a little example of that. So not H, that's what I'll put here. And we could take the homomorphism phi from Z2 to D4, and we could take 1 to S, right? So notice the image of phi in this case is the cyclic group generated by S inside of D4, which is just got the identity and then the reflection S, right? Yeah. So the image is abelian, but the whole codomain D4 is non-abelian, right? It's just we miss everything that would make the image not abelian. We don't land on it, right? Okay. So that's like an example of like how this might break down. Another thing is the range being abelian doesn't mean, or the image or range or whatever being abelian doesn't mean that the domain was abelian. We saw an example of that last time where you can like take D4 and essentially like squash all the rotations down to the identity and just leave the reflections or whatever. And the image will be Z2, which is abelian, even though the domain wasn't. So I won't redo that one because we did that last time. Okay. So what we want to do is prove this statement right here. So I'll box it in red. Like that. Let's see how we can do that. So proof. Let's suppose, so maybe we need some notation here. Maybe we'll call it like U and V. No, maybe X
and Y.
X and Y. What would the pre-image be if we had X and Y? And maybe X and Y. So let's suppose that X and Y are in phi of G. Right. So they're in the image. And notice that our goal is to show that phi of G is abelian. So what we want to show is that XY equals YX. Right? That would be the condition that we have. This is abelian if two arbitrary elements commute with each other. All right. So now let's unravel what it means to be in phi of G. So that's the first step, is to like unravel our hypothesis. So that means there exists two elements A and B in G such that phi of A equals X and phi of B equals Y. That's exactly what it means to be in the image, right? Now we're ready to do the calculation. So now maybe we'll like observe that Y can now be rewritten as phi of A, phi of B, right? By this up here being in the image. But now we can smash these together by the fact that phi is a homomorphism. So this is phi of AB. Let's write that because phi is a homomorphism. That's the defining characteristic of a homomorphism. But now that's equal to phi of BA. And that's because the domain is abelian. Right? So notice that switcheroo happened within G, which we assumed to be abelian. But now we can split this up again. This is phi of B, phi of A, and that's because phi is a homomorphism again. But finally, that's equal to y times x, just by renaming that back to what we had before. But, starting here and ending here is exactly what we wanted in order for this to be abelian, right? Okay. Cool. Okay, now let's show that cyclic, the cyclic thing. The cyclicity is preserved. Okay, now let's write it in words again, and then we'll write it with like functions as well. Yeah, I think it's useful to see both versions. So the homomorphic image of a cyclic group is cyclic. So that's how we could write that in words. And now with the way the book writes it, with like a defined function, it would go like this. So let's suppose G is cyclic and phi from G to H is a homomorphism. Then phi of G is cyclic. So I'll like box that in yellow. Okay, so let's look at the proof of this. So another thing, maybe like you could have the image of a non-cyclic group being cyclic, which we actually saw. We took the dihedral group last time and we like zeroed out all of the rotations and we ended up with a reflection. The reflective group is just like Z2, right? So if we had just Z2, well, that's cyclic, even though the domain was not cyclic, just by putting enough stuff in the kernel. Okay, so let's see how the proof of this can go. And now here, in this one, you want to like use the fact that G is cyclic to pull a generator. So since G is cyclic, we have a little g in big G such that a big G is equal to, well, it's generated by little g, right? That's the definition of being cyclic, is that you're generated by a single element. Now we want to show that phi of G is cyclic, and I think the best way to do that is really to make a guess. It's not much of a guess because it's like pretty obvious, but make a guess what the generator of phi of G should be, and then prove that that's the case. So that's what we'll do right here in blue. Blue's a good guessing color, right? What does that even mean? Okay, so our guess is that phi of G, the image of phi, is equal to the cyclic group generated by phi of little g. That kind of makes sense, right? If you just look at like phi being applied to both sides, and now notation is like a little bit different, but it seems like that should work, right? Yeah. So that'll be our claim. So maybe we could like change that guess to a claim. And then prove this claim. And just for good measure, we could prove that with double set inclusion. So let's first show the set inclusion that way. In other words, we want to start with something in phi of g and show that it's in the cyclic group generated by phi of little g. So let's do that. So let's suppose that x is in phi of g, right? But then that means that x equals phi of little a for a in G. But we know that G is generated by the element little g, but that tells us that a equals little g to the n for n in the integers, right? Again, like this being in here means that, right? Yeah. But now we can just mash these two facts together. So mashing these two facts together gives us that x is equal to phi of g to the n. But then using the fact that phi is a homomorphism, we can bring that exponent out. I think that was either like a Homer problem or that was like one of the properties of homomorphisms that was in one of the videos or something. So we can take this out and we have phi of g to the n. Exponents come out of homomorphisms. But notice that the fact that x equals phi of g to some power tells us that x is in the cyclic subgroup generated by phi of g. Right? This and this mean the same thing. Okay. So now let's do the other direction. So that would be the containment this way. So we want to take something over here and show that it's over here. So let's suppose x is, maybe we'll use y. So let's suppose that y is in the cyclic subgroup generated by phi of g. Right. But now that tells us that y equals phi of g to the m power for some integer m. That's the definition of being inside that cyclic group, right? But now we can do the same thing again. Notice that this is equal to phi of g to the m. We bring that inside because it's a homomorphism, right? But little g is inside of big G, right? That means little g to the m is inside of big G as well, right? But if little g to the m is inside of big G, then phi of little g to the m is inside of phi of big G. So that's because g to the m is inside of little g. But that's what we needed, right? We started with something in the right-hand side and we ended up with it being in the left-hand side. So we've shown containment both ways, which means that we've proven this claim. These two are equal. But these two being equal, well, this is cyclic over here. The right-hand side is cyclic, right? But that means that this is cyclic as well. Okay, cool. Cool. Okay, let's look at, we got some time. Let's get another one. Let's find. Was 11 assigned?
No, 14, 16, 18, 19.
Yeah, how about 14? Let's work on 14 for a little bit and then we'll go over it. It was muted here, so they didn't hear my rant. We just went deep in Rantsville over here, guys. You missed out. Where's my tab? I'm on the fringe, you know. Semester's long. Where's my chalk?
You are having roommates next year anyway.
Yeah, like they're giving us roommates.
All right. What do we say? 14?
Yeah.
Okay, we got G is a finite group.
They're over at the boundary zone.
We have N is a normal subgroup. And H is a subgroup of G mod N. And that's what it says. Prove that the inverse of H. So recall earlier we showed that the inverse image of a subgroup is a subgroup. We did that last time or the time before last. I don't remember exactly when. Is a subgroup of G of order. And we've got some order here. It's like H times N. Order of H times order of N. And phi goes from G to G mod N is, they call it the canonical homomorphism, but I'm going to call it the like canonical projection because that's like maybe slightly more universal way to write it. And what do we mean by this canonical projection? Well, we used it in the proof of a couple of the isomorphism theorems. This is the map that takes G to the coset Gn, like that. Okay, so there's some stuff that we don't have to do because we did it already, and that is this subgroup part is done. We did that last time or time before last. We proved that the preimage of a subgroup is a subgroup. So we just have to like count the number of elements in here. Okay, but there's a lucky thing here, and that is by the second or third isomorphism theorem. So I think it's the third isomorphism theorem says this. Subgroups of G mod N are of the form K mod N, where K, where N is normal in K, which is a subgroup of G. So K lives between G and N. Okay, so that's the third isomorphism theorem. So that tells us that this H, since H is a subgroup of G mod N, that quotient group, that tells us that H is of the form K mod N for, well, I'm going to write the same thing. N is normal in K, which is normal in, which is a subgroup of G, like that. And then furthermore, so further, this K, and this is also from the proof of the third isomorphism theorem, further, this K is actually the subgroup phi inverse of H. Okay. So now we can really do it. Notice that we have, from this over here, we have that the size of H is equal to the size of K mod N, but that's equal to the size of K over the size of N. That's by Lagrange's theorem. But like we said, which follows from the third isomorphism theorem, K is the inverse image of H. So this is the inverse image of H, but the size of that over the size of N. And now we can just multiply both sides by the size of N, right? So multiply this and this by the size of N, and we get the size of the inverse image of H is equal to the size of H times the size of N, which is what we wanted to show. So you can definitely do this from scratch, but if you do this from scratch, you're going to be essentially like reproducing the proof of the third isomorphism theorem. So this is one of those cases where it's really useful to like look at the results that we've been given. And there's a big hint built into this that we should be looking at the results that we've been given, because we're given a subgroup of a quotient group. And if you look through like the isomorphism theorems, there is one that has to do with the subgroup of a quotient group. So that should be inspiration to try to use that. Okay, so we're all set. The homework will be due on Tuesday. We're gonna introduce one more thing before the end of class, rings, but we're not gonna do much with them, just like basic definitions and stuff. So it'll actually feel like a step simpler because it'll be all of the like just basic definitions of this new thing. Whereas right now we've gotten into some pretty intense stuff with groups. So there'll be a couple of videos for that next time. And there won't be a homework for that, but it'll show up on the last test or whatever. Yeah. Okay, sick. So we seem good?
Yeah.
Okay, so I'll see you two in an hour. I'll post this if you guys want to watch it again at some point. Peace out, guys.